Okay, so last time we had discussed detonation shock dynamics and then just compared to some older calculations of some direct numerical simulations to DSD theory and also to the simple Huygens propagation where the propagation velocity of the detonation is constant. And so now we got this nice theory. Now, how is it actually used? Is that essentially how this is used is basically DSD theory is used to make a plot like this, where we know the position of the detonation front at say given points as a function of time. And so that's called a time of arrival plot. And so what we do if we know the field of the time of arrival, which is the time after some t equal to 0, that a detonation reaches, say, this point over here. And so what do we do with that information? Because this isn't really super practical yet. And so how they are used is they're used in a technique called programmed burn. And so say you have a crazy, say you're studying a crazy detonator, and a detonator is just a series of easy to ignite energetic materials that may not be the most energetic compounds in the world, but they will ignite fairly reliably. And then they are used to produce a massive shock wave that then ignites the actual explosive that you're interested in igniting. And so this here is actually based off of a sort of commercial detonator that you can buy. It's an RP80 for those who know that kind of stuff. And essentially the detonator here is a pellet of petin that's used to ignite a pellet of RDX. And then that produces a detonation through the RDX, which is then used to detonate the overall explosive charge. And then surrounding it, the petin in the RDX is a brass sleeve of some sort. And so say you wanted to analyze this in detail. And in theory, you could solve the reactive Navier-Stokes equations to actually solve for the detonation structure, the motion of the brass sleeve, and basically all that stuff. But that's not really practical because to do those sorts of calculations, you need to resolve the structure of the detonation itself. Now, I kept drawing these huge, something like this. So if you have the shock, you have the Z and D spike, and then you have the CJ point right here. And so I kept drawing these huge, but these are very thin, on the order of maybe tens of micrometers at most for most realistic explosives. So if you solve the full reactive Euler equations for the system, where you account for the chemical reaction in the full detonation structure, that's called a reactive burn. Unfortunately, for practical calculations, it's not practical to do a full reactive burn, except for maybe the simplest of charge configurations, where you have a perfectly spherical charge. For something like this, if you're looking at various design parameters, that's not practical because those calculations take quite a while to do. You have all of these different materials that you need to consider. And so basically, what is a cheaper way of doing this? And so, as I said before, that we could do a full DNS. In explosives context, those are DNS. It's not a direct numerical simulation from a turbulence point of view. But then the turbulence folks do not get full claim on the nomenclature DNS. And so, okay, so you could do that, but you could do the full reactive Euler equations if you have a reaction mechanism for all of these different compounds and some sort of stress law for the brass, and it would work, and it works just fine, and people do that. But those are very computationally intensive calculations. What if you want a more rapid fire type of solution? Well, that's actually where detonation shock dynamics comes in. And so what a program burn does is, rather than actually resolving the detonation front, you basically use the time of a rival plot that came out of DSD theory, and then you say, well, I have a detonator. I'm going to initiate this charge here, and then I know that, say, at time equal to 1 microsecond, that the detonation front is going to start here, and it's going to propagate maybe over to here. And then basically any point, then basically what you do is you take that time of arrival plot and basically set up your computational grid. And then basically, if the current time at a given point, say here, if t is equal to the time of arrival, or TOA, for that detonation there, you basically release the chemical energy that that is in that cell, and the idea is you basically, at that time, you basically flip the products to the reactants, and it turns out there's a bit more things that you have to do for that, but basically what that gives us is, that gives us the effect of the detonation curvature, without needing to do a full detailed reactive burn simulation. And so basically all you need to do is just basically run the calculation, and then say, if at this point here, the time of arrival is 0.1 microseconds, you basically run the calculation, and then at 0.1 microseconds, you would basically flip that point from unburned to burned. And there are a lot of practical considerations with this, but that's the idea of a program burn. They are very cheap, and for a lot of scenarios, they work well enough. And then for super detailed work, you have no choice but to do these full-blown direct numerical simulations. But basically, the whole idea, or the whole reason that detonation shock dynamics was developed, was actually to produce those time of arrival curves, so that you could develop a cheaper methodology for computing the detonation propagation through a structure, which is then tied to how the blast propagates from the explosive and things like that. Okay,
Hey,
and so
Professor,
yeah.
for the time of arrival for each point, how do they calculate what that time is? Do they get that from previous like DNS simulations?
No, they get that from detonation shock dynamics.
Okay.
So basically, so say here is the initial detonation location. And so what we do here is you basically propagate the surface, basically using detonation shock dynamics, you propagate the surface of the detonation for, say, I don't know, 0.1 microseconds. And then after 0.1 microseconds, the surface of the detonation is here. And so you know that basically at all of these points, the detonation arrived at 0.1 microseconds.
Okay.
And then you basically keep on doing that. And then if you do that for enough times, you get an entire field of times of arrivals.
Okay. All right.
Does does that make sense? Okay. And so that's basically how this is used. And you can do the same thing with a DNS if you want to. It just depends on the level of accuracy that you are looking for. But oftentimes, DSD theory is much cheaper to apply than a full-blown direct numerical simulation. I know Tom Jackson does a lot of DNS calculations. Braden, my student, is actually going to build the capability in our lab to do DNS calculations. And that gets really, really complicated because you need to consider all of the compressible solid mechanics and the very high strain rate and sort of plastic flow that occurs when you have 40 GPa pushing out the sides of the brass sleeve. It gets really complicated. And so a program burn is a much cheaper solution, which is practical for a lot of different applications. Okay, and then oftentimes, I'll just make a note here. Oftentimes, the time of arrival is stored in a burn table. Okay, so if you're ever working in this area and you hear the phrase burn table, that's just a table of basically a grid of points with the time of arrivals. And then there are some practical considerations. Is that I basically said the idea is if you have a point and you know that the detonation is actually going to run through that point at say 0.1 microseconds, you basically flip that point from unburned to burned. It turns out to for practical numerical considerations is you need to slow it down a bit so you don't flip it instantly. You basically start burning it at that time and then you sort of just say it burns, it takes 0.01 microseconds for basically the whole thing to burn. Otherwise, sort of weird things start to happen with the code. And there are a lot of numerical reasons for that, and I'm not going to get into that in this class. But this is basically one of the whole reasons for doing DSD theory. And this was heavily developed by the Department of Energy. And as I said before, I will let you use your imagination why the Department of Energy cares about very accurately timing detonations.
So, Professor, they use you use a table of basically, so it's like distance from the initiation point, basically, is what your table is, and that's all calculated in a table, and you use that table for the run that you're going to do.
Yep.
And so, how does geometry not impact that? Like, if I want to have some crazy surface instead of a cylinder or some crazy shape, how does it know to take in the right curvature?
Then basically what you have to do is you basically have to run a DSD calculation of your configuration. And so you do the
Okay.
so you do the DSD calculation of your configuration. That gives you the time of that gives you the burn table. And then you basically use that burn table in your blast code to more accurately predict that blast. Does that make sense?
Yeah, got it. So it's not like you can take DSD theory and apply, you have to run it for your geometry and then you can use it. Gotcha.
Yep.
Okay.
Yep. You basically have to run it for basically your geometry. And now codes like CTH and AL3D, they have program burns. But to my knowledge, they don't use DSD theory. They use pure Huygens theory.
It all propagates at the same velocity when you use
Yep.
program burn and CTH at least.
Yeah. And so most of them don't use DSD theory. I know Dr. Stewart has been sort of beating the drum of DSD theory for developing more, like precision devices. And so, yeah, because in the near field, in the far field, it probably doesn't matter that much because the sort of blast forgets about the details of basically how the detonation wave formed and and basically broke out of the surface. But in the near field, that makes a huge difference. And so there are certain applications where it is absolutely critical to know the precise timing of basically the detonation propagation and how it breaks out of the surface. Okay, and so that's just, I'm not going to get into this. We implemented program burn in our own code. And the concept is actually borderline trivial. There are a lot of little numerical details that you need to get it to work properly. And it turned out to be one of the hardest things that I took it upon myself to do that. And that was one of the hardest things I had to do is to get that working properly. So it's one of those things, it's easy in concept, but there are a lot of little gotchas and I can't possibly explain those all in a quick lecture. So I'm just giving you a really rough idea of how this works. Okay, and it's used in a lot of codes. CTH, AL3D, other little, and I shouldn't say little, those codes are huge. They're called hydro codes that basically do these types of things. I think a code called Shamrock has the same thing too. Okay, so are there any questions with that? Now, I am going to just mention a little aside when you're working with solid explosives, is that there are many equations of state that are used for the explosive because you're dealing with extremely high pressure. And so you need an equation of state for the gas that accounts for the high pressure effects. Because again, your density is so high that your gas density is on par with the solid. And so certainly non-ideal gas effects basically come into play. And one of the most common ones that is used in CTH and things like that is called JWL, or the Jones-Wilkins-Lee equation of state. It's one of the more simple explosive product equations of state, and there are tables of parameters available. Granted, they're ancient. Apparently, there's a bit of a story behind that table. I'll have you search for it. I'm not going to post it because basically the DOE actually Lawrence Livermore released that document that had JWL parameters for all kinds of explosives in the 1970s, and apparently DOD was not happy about that, and so they sort of pretend that document doesn't even exist. And so, but that document does exist. Granted, all the parameters needed for JWL to model blast for a given explosive, those are way out of date. And the modern version of that document is not publicly accessible. Okay, and so basically for JWL, essentially it is standard constant property ideal gas plus these crazy nonlinear barotropic terms. And basically what I mean by barotropic is that the pressure is a function of density only. And so even though these two terms here are complicated, it turns out in terms of the solution vector, they are a function only of the density, and everything else is constant. Okay, and so what you'll find with the explosives world is the equations of state are not as formalized as they are for the combustion world, and so they don't use compressibility factors and things like that. And in fact, with the way this equation of state is written, it'd be a bit of a nightmare to convert this into a compressibility factor. And often these equation of states are purely empirical. In fact, JWL, if you consider a blast, and here's the CJ point, and you're going to plot the sort of pressure as a function of rho. Essentially what they do is they just consider an isentropic expansion of the detonation products and basically fit those. And that's how, if you use a code called Cheetah, it can determine JWL parameters for you, because it uses a very complicated but more thermodynamically correct equation of state. And basically they compute the CJ point, isentropically expand it, and then basically fit all of these parameters so that you can use them as inputs for a CTH or some other blast modeling code. Okay, and so there are all these sort of parameters. It's a very nonlinear equation of state, and sort of one gotcha. The reason that another reason that you don't consider compressibility factors with explosive equations of state is that a lot of them aren't even thermodynamically consistent. JWL is one of them. Is that it does not satisfy all of Maxwell's relations, and so that is a big gotcha with these things. So they are intended for their one application. They are calibrated for their one application. And so use them only for that one application. You can't use JWL willy-nilly. It is meant for basically one purpose, and so use it for that one purpose. Okay, and so now, and then also oftentimes the same JWL form is used for the solid reactants. And so if you want to do a direct numerical simulation, you're not only going to need an equation of state for the products, but you're going to need an equation of state for the solid too. And so that also is going to be some nonlinear equation of state. And that is most often done by basically JWL but with different parameters. And one other gotcha with JWL and other explosive equations of state is that the parameters for them are a function of the explosive charge. So basically, if you run CTH or code like it, you'll see that for every different material, there are different products. And the reason for that being is that the products of, say, the Penton detonation are, say, a JWL gas, and the products of RDX detonation are a different JWL gas with different A's and B's and C's and things like that. And the reactants are a different JWL gas, and the reactants for Penton are yet another different JWL gas, or JWL, I should say, material. And unfortunately, fortunately, the form for all of these different materials for JWL is used for the products and the reactants, but they all have different constants. So you could have, if you consider a rate stick here, we have the reactants here, we have the products here, and where in the reaction zone where there is burning occurring, you have some in-between state. And so now we have an additional complication, is how do we mix multiple multiple JWL equations of state in the reaction zone? And it turns out there's no explicit mixing rule. You can't just sum the mass fractions times A and you get a mixture A. That does not work. And so the mixing of different JWL gases becomes extremely complicated, because you basically need to deal with these points here that are partially reactive. Is that they're basically halfway between they're basically partway between the reactants and the products. And so in this region here, you need to deal with a gas or a mixture of two different materials. Okay. And so, and the equations that govern this detonation, they're the same as the equations that that govern the detonation of a gas. They aren't any different, except for the only gotcha is that instead of all the species belonging to the same equation of state, and you have a mixture rule to account for the different species, for this explosive detonation, all of the different species have a completely different equation of state. And so what do we do with this when it's generalized to all the different species have a completely different equation of state? You can't mix them as easily as you do in a traditional combustion sense. Okay, so for example, for our detonator, you have JWL reactants, JWL products, air, that's an ideal gas, and you have brass, and there's very solid mechanical equations of state that you can use with varying complexity. And so now, say you have the horrible condition where at a grid point in your calculation, you have part JWL reactants, part JWL products, you have part air, and you also have part brass. And so now you need to find some sort of mixture state for all of these different equations of state. And so there are various assumptions for doing that, and one of the most common is to use what's called pressure temperature equilibration. So basically what you demand is that even though all of these different materials are basically present at the same point, just in different mass fractions, you demand that all of the materials agree on what the pressure is. So that is all of the different materials have the same pressure. And you also state, well, you know, then you also need to assume that all of the different materials agree to a common temperature. And so basically the process of finding that unique pressure and temperature, where basically all of these different materials can basically shake their hands and agree that yes, this is the pressure and temperature, that's called pressure temperature equilibration. And so basically what we demand is that we define that that the mixture sensible internal energy, or the internal, that mixture internal energy is equal to the sum of the mass fractions times the internal energy that is computed for species I. Okay, and this looks the same as it did for the normal sort of like gas laws, but here the caveat is that all of the different EIs have a completely different equation of state, completely different functional form, and you can't mix and match them like we did before. Then you also, and so the internal energy is known just from solving your governing equations. Then you demand that you use the law, or you use Amagat's law of partial volumes, and you basically state that the sum of the mass fraction times times the volume of basically each of the species equals the specific volume of the mixture. And you do know the specific volume of the mixture because through conservation of mass, you know density. And so basically, you use the equation of state for your guess pressure and temperature, and compute the specific volume for all of the different materials, then basically multiply them by basically yi and sum them up. And you know that the pressure and temperature is correct if the sum, if basically this sum is equal to the specific volume of the mixture, and this sum over here is equal to the internal energy of the internal energy of the mixture. And so, yeah, and so I basically already said this stuff here. And so this is a really nasty nonlinear equation solve here. And it's most commonly solved using a Newton-Raphson type, type method to find this combination of pressure and temperature, to find where the equation of state for all of the different materials can where they can basically shake hands. Okay, and so that's just a little caveat. And that's another reason people don't like reactive burn. I think in Bala's group, they did some JWL blasts for their former PSAP center. And they were just doing traditional blast work where you had just two equations of state, JWL products and air. And those are two completely different equations of state. You can't mix and match them like you do with most other, so you have to go through this formal PT equilibration process. And even though the mixed cells were only between the JBL products and the air, which is a very small portion of their calculation, I think, I can't remember the exact factor, but the PT equilibration process between air and JBL products increased the computation time by what, I think a factor of 2 or 3 or something like that. And so they came up with some tricks to get around that. So this PT equilibration is a very expensive computation. And it's very, and when a blast code breaks, it is normally during this step. And so it's challenging enough if you have 2 different materials. If you have 4 or 5 materials, it gets really complicated. And so basically giving it a starting guess for pressure and temperature, a good starting guess is important. And then also you do wind up with scenarios where you can have a solid in extreme tension, and that's negative pressure, and then that's adjacent to a gas, and the solid wants to be in tension, and the gas physically can't be in tension. And so in those sorts of scenarios, there's no way, it is impossible for them to agree on a common pressure. It's just not possible. So this area gets very complicated when you have to deal with these so-called mixed cells. Okay, so I'm just, I'm not going to go through the numerical details of doing that, but I'm just making you aware of this, is that even though an explosive involves a solid material, crazy equations of state, is that you still in principle solve the exact same equations, just that it is complicated by the fact that all of the different materials have a completely different equation of state. Okay. And then for explosives, you need a rate law. And unfortunately, they physically should be Arrhenius based. There is no reason that they aren't, or there's no physical reason that they should not be based on normal Arrhenius kinetics. But unfortunately, in the Z and D spike, where you really need to know what all the Arrhenius parameters are, the equations of state for solid material at those conditions are on so shaky ground that you don't really even know. You don't even really know you don't even know accurately what the temperature is. So if you have no idea what the temperature is, you have no way of basically predicting what an activation energy is. Even molecular dynamics, which everybody sort of, or most people think as this really super accurate, very accurate way of computing things, even all of the molecular potentials that are used for molecular dynamics that you could use to basically estimate these things, those are even questionable at the solid detonation like conditions, because they're just not tuned. There's just no good underlying theory to develop equations of state at 50 gigapascals. They just don't exist. And I know folks at Los Alamos and Livermore are actively working on that, and maybe they've made some ground on that in the past 10 years. But if they did, they're not sharing it. And so, but yeah. And so basically, you should, in principle, the chemical reactions that describe the detonation of a solid explosive should be Arrhenius based, but that's not reliable. So instead, they are completely empirical. And then they are usually pressure based, because again, you don't know the temperature, but yet you need some sort of controlling knob on the chemical reaction. And so and pressure a lot better than pressure is a lot easier to compute with an equation of state than the temperature, because again, to do the temperature, you need to know all the vibrational modes and all that stuff. And intermolecular potentials and all that stuff to do the temperature, and that is just extremely complicated, where the pressure is a lot easier to calculate from a molecular standpoint. And so almost all HE reaction models are basically global. They go from basically reactants goes to products. There's no reversal. I know Dr. Stewart, he's working on a two-step where he goes to some intermediates, goes to some products, but he is working on trying, but that's he has a specific idea in his mind that he wants to develop that for. And I'm not going to get into that here. Okay, but for a pressure based, there's a common one that's used for more theoretical work. And so this is the rate of the mass production rate, or the mass consumption rate of the reactants is given by this rate law here, where nu and n and k are just constants. Okay, and so this is just based on the CJ pressure, which again, from equilibrium thermodynamics, even if it's overdriven, even if the detonation is curved. And I think I have you using this form for your computer project one, just because it's really easy to work with. And there's a more sort of accurate one in terms of just getting the basic physics right, and that's called the Tarver ignition in growth model, where basically it breaks the sort of reaction into the solid reaction into a bunch of into three different points here. So if we consider a solid explosive here, and we're going to heat it to a condition or a pressure to where it's going to start to burn. Initially, what people hypothesize is that that a solid explosive is not perfectly 100% solid. There are some little empty sort of air gaps, between all the solid crystallites and things like that. And so those basically form as seed points to produce hotspots. So the first stage of the Tarver ignition in growth model is the ignition of these so-called hotspots. And that's given by this completely empirical rate law here, where AB and A and X are constants. Then you have all these little hotspots here, and now they need to grow and expand in size. And so those are the two different growth steps. I'm not sure physically why there are two growth steps. I would assume maybe after a point, the hotspots start growing into each other, and you need to consider that area. I'm not quite sure myself, but I think at the end of the day, these two different growth of the hotspots regimes are just used as empirical tuning parameters. And so it's a phenomenological model, meaning that it's not based on really super rigorous physics, is that they're just hypothesizing that there are these hotspots, and then those hotspots grow. And then they do a phenomenological derivation to get these sort of functional forms. And then all the different constants are determined via empiricism. And I'm not going to get into in this stuff in this class how they determine those, but those are often determined based on what's called a process called shock to detonation transition and matching experimental results of those. And so, but I'm not going to get into that in this class. If we do a day on detonation initiation, I will discuss what shock to detonation transition is. Okay, and so that's so the Tarver ignition and growth model is a very common one that you see being used too. And so note that that all of these parameters are tied to the equation of state. So if you have Tarver ignition and growth parameters that were developed for JWL, and you're switching to, and you want to examine them, and you want to examine the effect of a different equation of state, such as another one called the wide-ranging equation of state, then these Tarver ignition and growth parameters will not be the right ones, and so they are specific to an equation of state that they are calibrated for. If you want to use a different equation of state to model the same process for the same material, then you're going to have to retune these parameters. Okay, it's just the way it is. So are there any questions on that? Okay, so-
Professor,
Yeah,
could you scroll up a bit?
Yeah.
I had a question. So what are the bounds? The YP is that IG max? Ideal
that is basically G1 max. Is basically if the mass fraction of the products is between 0 and basically whatever this sort of constant is here, that's also a constant. You're basically assuming that the sort of bubbles are. I think he's assuming that the hotspots are growing basically independently, is they're not interacting with each other yet. Then basically after they start interacting, there's going to be some mass fraction where the hotspots start interacting, and that is this mass fraction here. And then you have a different sort of growth. Then there's a different growth regime, and so that's basically what that is. And so that's just G1 max, because you have basically, and G1 stands for growth stage 1. Okay.
Okay. And so it transitions from after it passes the Y mass fraction at G1, it transitions from ignition growth to growth 2.
Yep.
Okay.
Yeah, because our growth, and then basically all of these are implicitly 0 elsewhere. Okay, and so basically it first ignites, then it grows in stage 1, then it grows in stage 2.
Okay.
Does that make sense?
Yes, that makes sense. Thank you.
Yep. Yeah, and so you'll see this one being used quite often in sort of more detailed DNS style work. Okay, and so now there are unsteady effects of detonations. The Z&D model assumes steady flow, but what happens if we make it unsteady and just add this time derivative here? Does that make any changes? Because even in our Rankine-Hugoniot analysis, we assume steady flow. And so what are the effects of any unsteadiness? And so what people will do is they'll actually solve these transient equations, and then they'll just plot the shock pressure or the shock velocity or the leading shock velocity of the detonation as a function of time. And so if there is a steady solution to the detonation, and there is not, basically the shock pressure will start to oscillate in the beginning, then it'll eventually steady out to the computed CJ state. And I'll get into what tau is after a while. But for some various parameters, they find that there is no steady state solution. Is that the shock pressure keeps oscillating, and sometimes it sort of keeps growing too, and it gets worse and worse and worse. And so in these cases, the unsteady effects cannot be ignored. And these are perfectly 1D calculations. There's no multidimensional effects going on here. And so these one-dimensional detonations where there's no steady state and the shock pressure keeps oscillating, that's called a galloping detonation, because you can kind of see it's sort of galloping like you're on a horse. And this tau is a parameter that's been found that sort of characterizes it well. And tau is just given by the universal gas constant divided by the molecular weight times the activation temperature divided by dCj squared. And I don't know if they just messed around and found that that worked, or whether there was a sort of like Buckingham pi type thing that they did that found that that is a good parameter to sort of check. But anyways, if this tau parameter is 0.5 for your given material, or gas or solid for that matter, it'll stabilize if you mess with the detonation structure, it will decay down to a stable CJ velocity. And if tau is 0.54, you get the sort of stable, sort of almost sine wave thing. If tau is 0.55, you get a growing sine wave. And all these plots are available in John Lee's detonation phenomena book. If you increase tau further, you start to see really interesting patterns. If any of you have taken any nonlinear mechanics, there are these things called limit cycles, and eventually what will happen is, oops, tau is going up, going down. Oops. So is that basically the stable behavior it'll become quasi-steady, that you get a nice regular repeating pattern, but they're no longer sine waves. They have these really sort of peaky little spikes. And if you increase tau further, they start to become multimodal, and so they start to become very complex. And so again, these are all galloping detonations. And for some materials, like say gases, most gases at practical considerations will basically have some sort of galloping mode of detonation. But even though it is unsteady, the CJ, the Z and D theory does describe very well the average state. And so the average of the detonation velocities and shock pressures is actually the sort of CJ state, which is really, which are the Z and D state, which is actually very an amazing sort of result. And the theoreticians are still trying to figure out why that is. It's sort of very surprising. Now, in gases, there are called cellular detonations. Is that gases almost always exhibit multidimensional instabilities. So let me open it up here. So here's a calculation done where we have a hydrogen air detonation. So we just had we had a little hotspot here that ignited it. At the top here will be the, I believe, the pressure, and the bottom is the temperature. And so we just let it go, and a detonation forms. This here is a detonation, but notice that it's not nice and smooth like we kept drawing for the explosive charges. It is, for the gas, it is really bumpy. And those bumps are not numerical, they're physical. And if I pause it again, you see this sort of fairly regular repeating pattern of these little bumps and then these sort of depressions. And so these are called detonation cells. And almost all gases exhibit them. And in fact, for gases, they are almost always required to produce a stable detonation for a given configuration. Let's see where that is. And so, and here's just a movie that was made by Dr. Brian Taylor. And so with these cells here, oftentimes they're irregular, meaning they don't have a nice regular repeating pattern. And you see all these different leading shocks of the bumpy detonation where multiple shocks interact. Those are called triple points, and the pressure is really high there. And experimentally, what they do is they'll fill a tube with air, or they'll fill a tube with a detonable mixture of gas, a detonable mixture of gases, and then they'll take a thin sheet, and they'll basically put a layer of soot on it, a very loose layer of soot. And then what they find is that the high pressure in the triple points actually erodes and scores off some of that soot. And so those are called soot foils. And so when we compute the detonations is we basically often make numerical soot foils. And so this here is a gaseous cellular detonation. It's called irregular because you have big cells and little cells. This here was for hydrogen air. And so all gases do this, solid explosives do not do this. But for gases, this is extremely important to the propagation of a detonation. It's not an interesting factoid. It is crucial to their propagation. Okay, so let me get this back up. And so gases almost always exhibit these cellular instabilities. This is just a very poor drawing of one. Is you had these sort of flat portion here. Those are called the incident shocks. Those are moving slower at about 70 to 90% of DCJ. Then you had those bumps that sort of surged forward. Those are called Mach stems, and their velocity is about 1.1 to about 1.3 times DCJ. And then basically where this incident shock and the Mach stem meet, that's called a triple point. And these are the things that basically scour these soot off the walls to sort of make these soot foils. And then basically behind that, you have all these sort of transverse shocks bouncing up and down. Okay, and so just the gas dynamic structure here is very complex. There's really, it's very fascinating from a gas dynamics point of view. But I'm not going to get into the details of that in this class. And so I just sort of said before is that the motion of the triple points leaves these tracks. These are called smoke or soot foils. And then they characterize either the detonation cell width, like this, or the detonation cell height. And so whether a material is basically prone to this or not is characterized by this chi parameter here. And this chi is just the activation energy over the universal gas constant divided by the Z and D temperature behind the leading shock of the detonation. If chi is small, your mixture will not produce detonation cells. And so basically for explosives, the chi parameter is small. For whatever reason, it's small. And so that's sort of, from a mathematical point of view, that's sort of part of why high explosives do not produce these cells. You may be thinking, well, to produce these cells, you need a very compressible material. But I will remind you that at 60 GPa or 40 GPa, a solid material is extremely compressible. And so basically, at those conditions, the solid material flows like it basically flows like a fluid. Okay, and so if the chi parameter is 2, you produce these nice regular cells here. So this here is a numerical soot foil, just a track of the maximum pressure, and you see these nice regular cell patterns. Okay, and in this here, T star is the Z and D temperature. If they bump up the chi parameter to 7, you see very irregular cells. You see big cells, you see small cells, basically things like that. And the higher you make chi, the more and more irregular the detonation cells get. If you make chi too large, eventually one of these cells will become so large that it consumes the entire channel and the detonation dies. Okay, and now one note here is that even though Z and D theory is steady and 1D, it gives a very good average state. So even for these really bumpy detonations that are cellularly unstable, the average state is still very well described by Z&D theory, which is absolutely amazing given the really complicated structure of the detonation, and that even though we have all these transverse shocks, is that basically most of that transverse shock energy goes into propelling in one way or another, goes into propelling the leading shock, which is amazing. Okay, and so and the last note before we move on to propellants, which will start on Monday, is for gases. These, as I said before, these detonation cells are essential for most detonations to propagate stably. If the channel is too small, the detonation fails. It's for a different reason than for high explosives. And basically, this critical diameter of a tube, of a small tube, where that can stably produce a propagating gaseous detonation, is called D star. It's not called the critical diameter for a gas is different than the critical diameter for a high explosive charge. I know it's confusing. It's just because the gas detonation community and the explosive detonation community sort of grew up independently, so they have the same terminology for two completely different things. Okay, and so that's something you're going to have to get used to if you work with gases and solids. Okay, but anyways, to produce a stable detonation is that the diameter must be greater than D star, and D star is the size of these detonation cells, of the average detonation cell, divided by pi. And so basically, the channel needs to be big enough to basically normally fit at least one detonation cell. Is basically what the criterion is sort of roughly related to. And then if you want to find data on detonation cells and other parameters, this is sort of all this information is compiled at the Galcit detonation database at Caltech. So if you just Google Galcit detonation database, you'll find all kinds of information, a compilation of experimental data on detonation cell sizes and all sorts of other things. Okay, and so that's it for detonations, and we will start propellant combustion on Monday. And there is and the theory for that is not as clean as it is for detonations, and so we will not be going into propellant combustion in as much detail as we did with detonations. Okay, so that's it for today. Are there any questions?
Just a quick question. So at the end, you mentioned that D star, the critical diameter, is equal to lambda over pi, which is the detonation cell size. But does that mean that D star isn't a constant value, since the cell height can change based on different chi values as the cell is like
Yes. And
okay.
so yeah, so basically you can think of the different chi values are basically representative of basically different they are representative of different gases.
Okay.
Okay, and so you can think of this D star is that for, say, for hydrogen oxygen, that will stably propagate a detonation in like a 300-400 micrometer tube. But say for methane air, you might need like 10 centimeters.
Oh, okay. Oh, I see now. It's a function of activation energy and
Yep.
Z&D temperature. Okay, so
Yep.
that would be different for. Okay, thank you.
Yeah, because the Z&D temperature brings in the effect of the equation of state, and then the overall energy that is evolved by the detonation, or the heat of detonation, really, and then the activation energy brings in information from the chemical reaction.
And are those cells made up? It almost looks like a bunch of oblique shocks. Is that kind of how you would describe those cells, or?
No, they're not oblique shocks, because I know the Mach stem looks like it's oblique, but it's actually not. Is that the Mach stem is actually the strong portion. So if I share the screen again, let's see. So sort of qualitatively, they kind of look like this, right? This part that bumped forward, this here is actually a Mach stem, and this here is sort of the incident shock. And even though the shock is sort of angled, it is much stronger than this incident shock. So normally you think of oblique shocks as being weak, are being weaker than a normal shock wave. But here it's basically just the opposite. And sort of if you have to work in this area a lot to sort of see it. But essentially what happened here is you get these moving triple points, and they basically collide and make a very strong little point explosion. So you could think of this sort of bump forward is the sort of remnant of a point explosion produced by the collision of at least two different triple points. And you can see that in the movie, in the wherever that movie went. Let's see, where did that go? You can see that in this movie here. So here we see a Mach stem right here, and an incident shock here. And then I'm going to fast forward the movie. Here you see two triple points here that are about ready to collide. And now you see a new Mach stem forming that's basically a point explosion produced by the sort of collision of those two triple points. And then that Mach stem grows, and this process repeats and repeats and repeats. And the incident shock is basically too weak to burn the material rapidly enough, so you see the shock and the full product zone start to move farther apart. And so it takes it basically takes this sort of Mach stem to burn it completely. Does that make sense? So this is actually really, really complicated.
And then, so we're seeing what we're calling the Mach stem as this like DCJ factor, maybe 1.1 to 1.3. And is that because the higher pressure is influencing the chemical kinetics?
Yeah, so basically when the two triple points collide, the pressure and temperature are so high that you basically locally overdrove the detonation a tiny bit, right? And basically then you have this sort of, oops, whoa, I don't know what the hell happened. The iPad went nuts. So then it went nuts again. I'm not doing anything.
Nice.
You gonna be nice now? Sheesh. What the hell? Boy, the iPad really does not want to go to that. Wow. Anyways, so I'll have to make hand motions instead, I guess. Maybe go to a new thing to describe this. We'll just go. Whoa, it does it here too. I don't know what's going on. Okay, so you have this point, you have the incident shock here, and just
we
say
still see the video in front of what you're trying to sketch.
Okay. So we have the incident shock here, and another incident shock here, and we have two triple points here that are just about ready to collide right here. So when these two triple points collide, what they produce is a small little almost point explosion. There's some theoretical debate as to whether it's really a point explosion or not. I'm not going to get into that here. You'll find if you work in detonations is that the detonation community is a very feisty community. There's a lot of disagreement on things. And then part of the reason I train my students so hard is that they will have to deal with very stern sort of Russian people and basically Russian physicists who have their own ideas. And so you have to learn how to sort of defend your ideas from them. Anyways, so the triple points collide. Then after they collide, the P and T of the reactants is very high. Okay, and so basically they're so high that they sort of react almost instantly. And when they react almost instantly, what is produced is a little explosion. Okay, and so this little explosion is like a curved overdriven detonation front, and it kind of follows the DCG rule, or it kind of follows DSD rules a bit. Is that it's basically highly curved, and so it sort of slows down. So as it expands, it basically slows down a bit, and then basically, and so yeah, and so basically, due to the high initial temperature and pressure when these triple points collide, you produce a very locally overdriven detonation that expands radially. But again, just due to the fact of that you have the curved detonation that's actually slowing it down, and you have the fact that an overdriven detonation is not stable, is that basically as this expands out, due to those two effects, this little bump on the detonation basically slows down and stops expanding relative to the propagating incident shocks. And then it slows down enough to where eventually the detonation here fails, and it becomes the incident shock. Again, it's really complicated, but it's actually very interesting and sort of beautiful gas dynamics. Okay, I hope that answers your sort of question.
Yeah, that did. Thank you.
Yeah, I was just sort of bringing them up because for gases, these detonation cells are really crucial to the stable propagation of a detonation. For solids, they just don't occur because that these sort of chi parameter is in a regime where they just don't exist for a solid.
You see that geometry so often, that kind of like diamond crossing geometry. You see that behind rocket motors, and you see it, in warhead detonations on sides. It just seems like a pattern that keeps coming up. It looks like even the characteristics when you
Yeah.
left and right characteristics.
It's just what causes the Mach diamonds in the plume of a rocket and these detonation cell patterns are completely different. Yeah, they are completely unrelated, but you are right. You see these sort of diamondy patterns quite often in various applications. Okay, are there any other questions? And so here I'm just bringing this to your attention, just that these cells are crucial for gas phase detonations, and they're crucial for if you're looking into rotating detonation engines too, where you don't have a solidly confined gaseous detonation. It's sort of semi-confined, and that stuff gets very complicated, and it's still a topic of research to this day. But are there any other questions? We've went quite long, so, but I'll be happy to answer them if you got them.
Nothing on this, but as far as just like the class goes for these class projects, I guess we at least have 7 people or 6 people in the class or 8 people in the class. So we're good with groups of 4 or.
Yep. Yeah, no, I think the groups are set, so.
Okay. Groups are all set. All right.
Okay, if there are no more questions, I guess that's it. I will